Okay, it is time for the long-awaited AP Chemistry review. It's crazy. I'm gonna be completely honest with you. AP Chem is one of my most scary APs, not gonna lie. Because I know physics, I know math, but chemistry? Come on. Hello everybody, I'm Carrara, and today we're going to be doing Unit 1 of the AP Chem curriculum, which, as you can see on the screen, is atomic structures and properties, and we're going to cover all that nonsense. So, as you can probably tell, we're going to start with moles and molar mass nonsense. Now, because AP Chem is AP Chem, and you should probably be at some level of proficiency at chem when you're taking the test, I'm not going to go over all the neutron, proton, electron nonsense. Just know you got your protons, which are positive, you got your electrons, which are negative, and you got your neutrons, which are just boring and don't have a charge. And basically, of course, on the periodic table, we got our beautiful dynamic P table over here. Look at it, change color, beautiful. But the point is, like, these numbers over here are obviously the protons, and then you got your atomic masses over here. So basically, atomic masses are the best way to introduce the point of a mole. What the heck is a mole? No, it's not like the beautifully cute. Well, actually, they're not really cute. Have you seen a star-nosed mole or a naked mole rat? They look disgusting. But the point is, what a mole basically means is it's a number of, like, atoms. It's basically like, if you have a dozen eggs, it's 12, right? A mole means the most arbitrary number, 6.02 times 10 to the 23. And you should probably know this, because you do not want to be, like, checking your formula sheet every time you want to check what a mole is. Now, like, honestly, the number itself is not super useful, but basically what it lets you do is it lets you convert from atomic mass units, which is basically like a proton has one atomic mass unit, a neutron has one atomic mass unit, it converts that to grams. That's literally all you gotta know about moles. It basically converts grams to atomic mass units. So basically we know that if you have one molecule of, like, nitrogen, let's say, any boy over here, basically it's gonna have only 14 AMUs, and you can't measure like 14 AMUs of nitrogen. That just doesn't work, okay? But you can measure 14 grams. But basically the point of the Avogadro's number, which is 6.02 times 10 to the 23, is that if you have 14 grams of nitrogen, you could tell exactly how many molecules there are in it. We know that there's exactly 1 mole of nitrogen, because we know that in order to get from 1 molecule, which is 14 AMU, in order to get to grams, from 14 AMU to 14 grams, you have to multiply it by 1 mole. Now the reason why this is useful, this concept of, like, moles, is because it doesn't matter how many grams of something you have, right? If you have, like, let's say that 1 feather reacts with 1 rock, right? Make a rock feather, sure, why not? So let's say you have 5 grams of feathers and 5 grams of rock. Obviously, there's more feathers in 5 grams than there are rocks in 5 grams. So, like, you're gonna have way extra feathers. And, like, the 5 grams didn't tell us anything. We have to know how many feathers there are, not how much they weigh. So that's why moles are useful, because it tells you how many there are. Okay, so basically, like, this right now is telling us the AMU of each atom. But you can also think of it as grams per mole, because we know that AMU, to get to grams, we multiply by mole. So AMU times mole is equal to gram. So if we want grams per mole, which is basically our molar mass, right? Mass over mole, then that's just equal to an AMU. So essentially, basically what I'm trying to say is that you could think of these numbers underneath all these letters as molar mass, right? So the easiest way to think of stuff in AP Chem is just think of it as a ratio of units. So an AMU is a gram over mole. Like, if you want to get from gram over mole to gram, you have to multiply by moles, and that way, like, it just makes your thought process so much easier, because you know exactly what you have to multiply to get your answer. If your answer is in grams, multiply by moles. If your answer is a mole, then you have to do grams over moles, and then you get moles. Okay, quick examples. Alright, let's say we have like 25 grams of calcium. Okay, then if we want to find out how many moles, we have to do over 40.08 grams per mole. You know why? Because if we cancel out the units, moles gets into the numerator, and we want moles. So this makes so much sense. And 25 over 40.08 gives us 0.624 moles. Epic. And if we want to convert from moles to molecules, we just use our same conversion factor. Just think of everything as conversion factors. 0.624 times 6.02 times 10 to the 23 molecules per mole. And boom, we have, what is 6.02 times 0.624? 3.76 times 10 to the 23 molecules. Because see, like, if we had moles here, moles cancels out, you're left with molecules, and that's what we wanted. Very cool. Okay, that's basically all you gotta know about like atomic mass and what it means and what moles are. Okay. Alright, now we gotta talk about isotopes. You know that an isotope is basically just an atom with the same number of protons but different number of neutrons, right? Because it's the same element but it just has a different mass. So just to annoy us, right, these elements just have to have different isotopes in nature, right? So like, bruh, what are all these random decimal points doing? Well, basically what this is the average atomic mass of all the fluorine atoms in the world. So clearly nature is not paying attention to the Declaration of Independence or Constitution, whatever. I don't pay attention to NAPUSH, I'm sorry, but like it didn't pay attention to the fact that all men are created equal, and it made isotopes unequal. God dang it. But basically the point is, like, some isotopes are more common than others. So in order to find these decimal things, you gotta like take the weighted average of the components, like the different isotopes. So just like if you have more of a certain type of isotope, its weight matters more. So why don't we just search up relative abundance of carbon isotopes, why not? And then we will go to Wikipedia, because Wikipedia is the most viable source of information. Alright, so basically this gives us our abundance right here. So essentially, if we had 100 carbon atoms, right? 98.9 of them, which doesn't make any sense, but we're still going to go with it, 98.9 of them are going to be carbon 12, meaning they have 6 protons, 6 neutrons. Okay, and then 1.1 of them are going to be carbon 13 with 1 more neutron. Okay, so we have 98.9 of them that weigh 12 AMU, then we basically have a total weight for all of those ones over there to be 98.9 times 12, right? And basically to find an average, you have to take the total amount of weight divided by the total number of molecules, or atoms in this case. So this is the total amount for carbon 12, then what is the total amount of weight for the carbon 13? There are 1.1 of them, right? And we have a weight of 13 AMU. And then that's the total weight of over all of the carbon atoms in our 100 carbon sample. And then we had to divide by the total number of molecules, which is just 100. And what will this give us? Let us see. Alright, it gives us 12.011. Wait a minute. Where did I see that before? That's right, you saw it in the periodic table. Let me show you just to flex my epic skills. Look at that, 12.011. We calculated from scratch. Look at that flex. Okay, I know how to calculate relative abundances. No, wait, what is it? Average atomic mass. I know the difference between... Okay, I'm just going to stop there. But apparently, the AP exam does not want to stop there. It's not going to just stop at making you calculate the thing from scratch. It's going to actually show you it in a graph. So basically, what we got to do is we got to explain the concept of mass spectrometry. So basically, let's say you got a little mix of like random isotopes. Okay, you got some carbon 13 spliced in there. You got some carbon 12. They're just hanging around here. They're all normal carbon atoms. So now what the first thing that the mass spectrometer does, it goes in here and it slams some electrons into these boys relentlessly. Okay, it's like a massacre. It's like the Boston Massacre, except it's massacring them with electrons and it doesn't kill them. See, I did pay attention in APUSH. Okay, come on. So basically what the massacre actually does, instead of killing them, is it turns them into ions. So now they actually have charges. It doesn't really matter whether they're plus or minus charges, but they basically have some charge. I'm not exactly sure what it is for carbon. But anyway, they're charged, that is the point. And basically what these charged particles are done, are they're sped up. They're like slammed through an electric field. They go super speedy. And then they enter a magnetic field. Wow. So now you have a magnetic field, right? You slam the electrons through, basically, and a magnetic field exerts a force proportional to your charge. So anyway, these ions pass through the electric field. The ones that are more charged get deflected even more. However, the more massive ones get deflected less because it's harder to move a more massive object. So basically, then they go like this, right? They get deflected. Some get deflected more, some get deflected less, like that. Okay. And then they all go into a certain detector that's over here. Boom, they hit the detector. Boom, they hit the detector. Boom, they hit the detector. And basically, the ones that got deflected the least are going to hit at the top. The ones that get deflected the most are going to hit at the bottom. And basically, the ones with the highest charge to mass ratio are going to get deflected the most. Okay, so basically, what you can take away from this, without knowing the entire workings of a mass spectrometer, is that it basically tells you the ratio of charge to mass. And basically what they do on the AP exam is they take it and put it in a chart, and they basically give you the data there. So they got your charge to mass ratio over here, or actually they usually do mass to charge, and then they do your relative abundance. Let's say some of the isotopes become +1 charge, right? There's going to be some from 12, there's going to be some from carbon 13. So obviously, if they both have a charge of +1, then like the carbon 13 ions are going to have a higher mass to charge ratio because they have more mass. However, there will be less of them detected, so there'll only be like this many. This is like a number of carbon 13 atoms that hit the detector. However, at a lower mass to charge ratio, which is your carbon 12, there's going to be way more of them. And essentially, like usually this will be out of 100%, and then it'll give you 98.9%, and then 1.1 over here. So, like, a silly mistake that a lot of people make is that they don't pay attention to the axes. Make sure that this is mass over charge. If it's mass over charge, you gotta make sure you know what the charge is before you find out what the mass of the isotopes is. But, if you find out what the mass of each isotope is, we find that this one's 12 and this one's 13, then we could apply our same calculation to find the actual average atomic mass. So, know how to read mass spectrometry data is important. The y-axis could also be relative abundance, okay? And basically what that does is it basically does everything relative to the highest peak. So, in this case, carbon 12 is the highest peak, and then this peak would be how much is 1.1% of 98.9%. Like, how much is it relative to the carbon, and then I'll give it here. It's still basically 1.1% because, like, 98.9 is so big. So this would still be 1.1 over here, about a little bit bigger though. If you're given relative abundances, to get the original abundance, you basically just do like 1.1 over the total, which is 1.1 plus 100. Okay. Or actually, you could literally just do that regardless. This is just a good rule to know. You basically do my percentage over the sum of all the percentages of all the other ones. Okay, that's all you gotta know for mass spectrometry and isotopes. Moving on. Dalton's laws. Okay, what are Dalton's laws? Basically what Dalton says is, this epic guy, Dalton. Okay, he looks kind of like this. Basically what he said is, the first thing is that, like, atoms are the smallest unit of stuff. Then he also said that mass is conserved. Alright, this stuff is pretty common sense. Maybe not for him, because this is, like, ancient. But yeah, just know this stuff. Okay, and then another thing he said is that compounds have a characteristic ratio of, like, atoms. So basically, if you have pure H2O, every single molecule in that like substance is going to have the same ratio of hydrogen to oxygen. No matter which part of that substance you take, it's going to have the same ratio. And basically that's called the law of constant composition. Alright, now that we know that the law of constant composition exists, what we could basically do is start writing out formulas to represent compounds. So basically, let's just go over really quick like what makes up different types of materials. You basically got your elements, which are individual pure substances that are made up of only one element, right? Then you got compounds, which are pure substances, of course, but they're made up of multiple elements. Then you got your mixtures, which are made up of multiple compounds. They're not bonded to each other, like, covalently, but they are together in the same mixture. And then within mixtures, you got, like, solutions, you got your suspensions, blah, blah, whatever. We're not talking about that now. We're only focused on compounds right now. So, yeah, the point is there's other stuff, but basically, right now we're talking about compounds. So basically, to represent compounds, the first thing you gotta know is their chemical formula, which is basically exactly what their molecule is. So benzene is a pretty good example, right? You got benzene, this boy over here. So basically, this is called the structural formula of benzene, and it basically shows you the bonds. Now, this isn't a great structural formula because the structural formula should show you the 3D representation, like whether it comes out at you or comes in at you, but I'm too lazy for that nonsense. But that's not the point. Who cares how lazy I am? We got to do the important stuff. So chemical formula is basically, you write out the number of each element in the molecule. So basically you got 6 carbons, epic, so we're going to write C, which is the symbol for carbon, then 6, and then we got 6 hydrogens, H6. Nice, we got a chemical formula. Now we got to convert this to an empirical formula, which basically reduces everything to so that, like, the smallest numbers possible, such that they're not fractions though. So in this case, literally, we could just divide everything by 6, and we got CH. You have to make sure that your proportions are the same. Like, if you want to check whether your empirical formula is right, just make sure that you don't have any fractions, and if you multiply it by some number, it gets to the actual formula. Okay, there is some nonsense about dealing with empirical formulas, but we will wait until we get to stoichiometry to talk about that. I'm pretty sure we'll talk about that in the next unit, so that should be it. Oops, let's label our diagram. So this is called structural, right? This over here is called chemical, and the most reduced one is called empirical. Alright, now that we got that down, we got to talk about ions. So basically, your atom looks like this, right? You got a nice little nucleus that's positively charged. Then you got a bunch of electrons swirling around like cool kids over here. Boom, 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 boom. Another one. Epic. Okay. So basically, electrons kind of look like shells. They're technically not in shells because there's orbitals, because of the probability nonsense. But you can basically think of it as shells, as in, like, it increases in energy. So basically, your outermost energy level is called your valence energy level, or your valence shell of electrons. And basically, the only thing that is really important about an atom is valence electron. Like, no one cares about the guys on the inside, okay? Those guys are boring. So in this particular atom, we got 6 electrons, okay? So All atoms want to make 8 electrons, so this ion is going to get 2 electrons in order to make 8, so it's going to have a 2+ charge. Just kidding, I know that electrons are negative, 2- charge, there we go. So this boy is going to make a 2- charge. Similarly, if you have 7, then it would be 1-. If you have like only 2 electrons, they would want to lose those 2 electrons to get to empty subshell instead, and it would be 2+. So basically the 2 things you got to remember is the negative ions are anions, and then 2+ is a cation because it's positive. And the way you remember this is cats are, you guessed it, the epicest pun of the century, positive. Wow, that's some beautiful stuff, not gonna lie. Even I could have thought of that myself. And I am the best pun maker in the universe. Alright, so some atoms are cool and they like giving away their electrons. Or maybe, well, they're kind of selfish, honestly, because they just want to get to that beautiful 8-pack electrons. But they do give away their electrons sometimes, or sometimes they snatch it from others, which is not as cool, but like still. So, in the case of sodium, right, let us look at sodium. So sodium is over here, right, and basically, if you're on the leftmost column of the periodic table, you basically have 1 valence electron. So, sodium got 1 valence electron hanging out over here, and then on the other side is 1 from the right side of the periodic table, so it has 1 valence, or it's like 7 valence electrons. Alright, now neither of these guys have a full outer shell, dude. Like, chlorine's missing 1, sodium has an extra 1, god dang it. But they want to help each other out, so sodium gives it an electron, and boom, that electron goes there. Chlorine becomes negative, sodium becomes positive, and now they're attracted to each other because opposites attract. Well, I guess they both look hotter now that they have their full outer shells, but that's not the point. So this is basically called an ionic bond. Of course, the other type of bond is basically covalent bond, which basically is where, like, if hydrogen had 1 extra electron and chlorine had 1 missing electron, they basically share their electrons so that they both are happy. And that is what a covalent bond is. But we are talking about ions, okay? So basically, if a bunch of things come together and make ionic bonds with each other, they're called an ionic compound, right? And these guys are the easiest to name. So we'll just go around and name them really quick. So if you have NaCl, that's basically going to be, you take the cation, which is sodium, and then you put the anion on the back, and you say chlor, except you end with the ide. Okay, cool. It doesn't even matter if it's like Ba, which has 2 valence electrons, and Cl2. You know that it's Cl2 because barium has 2 extras, Cl only has 1 open slot, so in order to give away all its electrons, it has to bind with 2 chlorine atoms. So, barium chloride, you don't even care how many there are, it doesn't matter. The only thing that matters is the actual identity of them, except when they are metals, transition metals. So if they're in here, they don't have a necessary 1 type of charge that they could have. So in this case, like if you have FeCl2, iron is not always 2+, okay? So that is why you have to say iron 2 chloride. Okay, don't forget the 2 or you're gonna get roasted. Iron could also be 3, so if it was FeCl3, it would be iron 3 chloride. But ionic compounds are easy to name, so that's literally all the rules you gotta know. But you do have to know the names of polyatomic ions. Okay, boo, I'm sorry, but you do have to know it. I'm sorry. I can't tell it to you in any other way. Alright, here's basically all of them, but like, I unfortunately don't have a good way of remembering them. I just smashed it into my head before the nomenclature test on mine, so I don't know how to help you here. Like, the only, like, pattern you could draw here is, like, if you have, your normal chlorate is ClO3-, right? So that means that your chlorite is gonna have 1 less, because it ends with an ite instead of an 8. And then, if you even have less oxygen, it's gonna be hypo, because hypo means less, and then per is like hyper, except they just cut off the HY for no reason, and it has 1 more oxygen. Okay, because this is a review and this is not a well planned out syllabus or any nonsense like that, we are gonna talk about electron configurations after talking about valence electron. Oh, actually, it's not a horrible shift in perspective. Well, okay, who cares? We're talking about electron configurations now. So, basically what atoms have, is they have orbitals surrounding them, right? And electrons fall into orbitals. But orbitals only have 2 electrons per orbital, okay? That's what Pauli exclusion principle says. Then how the heck do you get a shell with 8 electrons? That doesn't make any sense. Well, my friends, shells could have multiple electrons in them. So basically you have to know that there's 3 subdivisions for orbitals, okay? You got your N, which is your energy level. And this is what you guys like to call shells. So essentially if you want 8 valence electrons, you want to have 8 in your X energy level, okay? Then you got L, which is basically whether or not it's S, P, D, or F. And basically these are just different shapes of orbitals. Like S is a spherical orbital and it's the lowest energy orbital. Then you got p orbitals, which are like dumbbell shaped, and they are slightly more energetic than d is a different orbital. They're more d orbitals than p orbitals, but they're less energetic, and so on and so forth. If you want to be fancy, this is called the principal quantum number, n. Second one's called like the azimuthal, if I'm not mistaken, yes sir. The next one is called m. So basically m tells you the orientation of the orbital, right? Because the s orbital only has one s orbital per energy level, right? So there's only one possible orientation. So the m for each s orbital is just going to be 0, because that's the only possible orientation for it. However, if you have L is equal to 1, which means it corresponds to p orbitals, there are multiple p orbitals in each sublevel. Or however, if your L is equal to 1, which means it's a p orbital, there could be multiple p orbitals in each energy level. So that's why m could either be 1, 0, or negative 1. So like, this corresponds to 0, 1, 2, 3, and then basically m goes from 0, plus or minus 1, dot dot dot, all the way to plus or minus L. So that's how you remember quickly how many orbitals are in each energy level or sublevels. So L is basically your sublevels, right? So if the question's like how many orbitals are in the d subshell, you could literally just say m goes from 0 to plus or minus 2. So you go from negative 2 to 2. There's 5 orbitals there. And then this is just called the magnetic one. And then last but not least, you got your spin, okay? And this could just be plus or minus 1/2. That's the easiest one to remember because it's basically saying that there's 2 electrons per orbital. Very cool. And it's basically why the Pauli exclusion principle exists. You can't have 2 of the same s in each orbital. So if there's only 2 possible values for s, you can only have 2 electrons per orbital. So if it asks how many electrons are in the d orbital, we take the number of orbitals, which is 5, and you multiply by 2, and you get 10 orbitals. Okay, epic. Now that we've got down all the quantum numbers, we can basically start talking about electron configurations, okay? Alright, so the easiest way to find electron configurations is literally just to look at the periodic table. Like, there's a bunch of random stupid rules for it, but doing it from the periodic table is just the fastest way to do it. But before we get into that, let us just explain the different rules, because why not? So you got Hund's, which basically says if you have these orbitals over here, like these are all p orbitals, let's say, then your electrons will first try to fill all the spaces without sitting to each other because they're not very good at social stuff like me. Do they even look like me? What the heck? But anyway, the point is they don't sit next to each other, and then if you have to add more electrons, then they start sitting next to each other when they absolutely have to. So that's the order in which they fill the bus. Basically like the people sitting in the bus rule. Then you got Aufbau, which basically tells you the order in which the energy levels are filled. It's basically, you want to fill the lowest energy levels to the highest energy levels, and basically the actual way you do that is called Madelung's rule. That tells you the exact order. Aufbau is just lowest to highest energy level, and then this one tells you which ones are the actual lowest energy level. But you don't really learn this one in AP Chem, not very useful. But anyways, Aufbau you literally don't even have to worry about it because the periodic table tells you everything. Okay, so let's figure it out. So basically energy levels correspond to rows in the periodic table basically. And then as you go from each element to the next, you have to add one more electron each time. So your first hydrogen is just going to have one electron, and that goes in the lowest energy sublevel, which has the lowest quantum numbers, which are your N, L, M, and S. And that's basically going to be 0 for all of them. And that's just the 1s orbital. So you're going to have one electron in the 1s orbital. Then helium adds another one, but this one could take another orbital or electron in it, so we add 1s2. Then we go to lithium, but 1s can't hold anymore. But now we're also on the second row, so we have to add another orbital. So our next orbital, the lowest level, is 2s. And then lithium has 1, but then when we go to beryllium, it becomes 2, and then we go on to boron. Now, boron, we can't fit anything into s anymore, but we're still on the 2 level, so we can't do a 2s again. That doesn't make sense. So we had to move up a different quantum number, which is basically our L. And now we go from s, we go to the next level, which is going to be p. So we got 2p. And then we only have 1, we've only added 1 so far. Then to get to carbon, we add another 1, then to nitrogen, 3, and then so on and so forth, until you get to neon, which becomes 6. Wait a minute, there's only 6 in the last one. How is neon a noble gas? Shouldn't it have a full valence electron? What the heck? Well, basically, your valence shell is all this entire part. So, all of them that have the highest number over here. So you had to sum 2 plus 6, and wow, it has 8. Just as we expected. And then we do 3s2 for magnesium, then 2p6 for argon. Okay. And now we do another, whoops, that's 3p6. And then we go to 4s2, but now we have a completely different thing. This is not the p area. Well, let me just break it down for you. Okay, so we have this part as the s. Okay, we already get that. We get the p, but then what the heck is this? What's this boys over here? Basically, these fill the d sublevel. But the d sublevel is weird because it basically shifts everything up one, because the D level is actually not that energetic. So even though this is row 4, we put it in the 3D level. So scandium, we're going to add another electron from calcium. We're going to add another electron, so it's going to become 3D instead of 4D, 3D1. And then if we go to zinc, we have 10 electrons added from calcium, so it becomes 3D10 for zinc. Alright, so now that we know how to deal with the D block, I'll teach you how to deal with the F block later, but let's first learn noble gas notation so I don't have to write down the whole silly electron configuration every time, okay? Basically, if you want to put calcium, you can literally take the earliest noble gas before it, put it in braces, argon, and then start the electron configuration from there. So after argon, you had to add 2s or 4s2, and you get calcium. Alright, epic. So now, let us figure out how to do lanthanum, okay? That is basically going to be, what's the first one? Xenon. Then we have to add in our 6s2 over here, and now we are on the F block. So it gets shifted up 2, so we're at 6, but we shift up 2, now we're at 4F, and it's only 1. Epic! There's some weird stuff with the F block. I wouldn't worry too much about it because it's probably not going to be on the AP exam. But yeah, it's pretty cool. You don't have to worry about the exact workings of the F block, but you can know a little basics. Alright, and lastly, the exception. Okay, basically, it's just half shells and full shells for the D block, right? So if you have like 3D4, right? A D subshell could have 10 electrons. And doesn't it just feel bad to be at 4 electrons and just 1 off from half a subshell? Come on, man. So basically, what has 4 D electrons? Chromium does, right? So basically, chromium's like, I don't like this half subshell. We're gonna snatch from S. Because if I take one from S, right, then I become 1 in my S orbital, and that's half filled, that's good. And then my D orbital also gets half filled, so it's a win-win situation. So, like, you might expect chromium to be argon, 4s2, 3d4. But no, it snatches an S electron, it becomes 3d5. And then similarly, for copper, it doesn't want to be almost to a full D subshell level. Come on! A full D sublevel, that would be amazing. So what copper does is it takes, instead of being AR4s2 3d9, it takes one and becomes a 10. Wow, yo. Don't forget the exceptions. They trolled me so hard on the actual test. Dude, I missed like 6 points in my AP Chem test. It was so bad. Alright, that was kind of big brain. Holy. Alright, now that we understand electron configurations, basically, if we only look at the valence shell, it often asks you how many unpaired electrons are there, right? So let's just do the example of sulfur, right? So you have neon, and then you have 3s2 and 3p6. Okay, so you have your s orbitals, 3s over here, and that's just going to be up, down. Then you have p, 3p, and there's 3 of them. So basically, oh, we have 4. Bro, I'm trolling. Okay, so we have 4 electrons. Okay, so we first add our first one. The next one doesn't want to sit next to him because the first guy is a troll. Then it goes to the next one, and then the fourth guy finally has to sit next to it, so boom. So there are 2 unpaired electrons, very cool. And basically, if a transition metal has unpaired electrons, it makes colors. Okay, so that's another cool thing to know. But what does it mean to have unpaired electrons? Basically, there's 2 types of magnetism. I don't even know whether they're on the AP exam, but you might as well know it. Paramagnetism is basically unpaired, and just like it says para, right? So it's like almost with something, like parallel. It's basically going to go attracted into magnetic field. And then diamagnetism means paired. All the electrons are paired, and then it repels magnetic field. We're almost done, guys. We're almost done. We basically got to talk about photoelectron spectroscopy, and we got to talk about periodic trends, which shouldn't take too long. Alright, so photoelectron spectroscopy. So if you shine a light on an atom, right, it excites the electrons, and eventually if you excite the electron enough, it'll just get yanked off the atom. However, if it was really hard to excite the atom's gonna move a lot slower because you had less extra energy to make it start moving. You had to spend all the energy on getting it out of the atom, not actually making it move. So basically what photon-electron spectroscopy does is, or photoelectron spectroscopy, is it basically shines a bunch of photons on an electron, it snatches all the electrons off the atoms, and basically the ones that are easier to snatch off are moving super fast, and the ones that are harder to take off move super slow. And then ultimately you could have a graph of how many of each energy, or how many of each speed were hitting the actual frame. So let's find a photoelectron spectroscopy data somewhere. Alright, so this is a pretty good example. No, why are you so small, bro? There we go. So basically, you can notice that the potential energy is decreasing as you go here. So the ones with the highest potential energy are over here. And basically, like, you could think of it as the ones that are closest to the atom are held the most tightly, right? So they're so hard to pull them out. So they have the highest potential energy. So the ones closer to the atom, the electrons that are closer to the atom are here, and the ones that are farther are here. And we also know that things within the same orbital have the same energy. And things within the same subshell, like S or P, also have the same energy. So this one's the closest to the atom. So obviously, this is just going to be your first subshell. So 1s. So this one's the next closest, which is going to be 2s, then you got your 2p, then you got your 3s. And you could tell, like, the height is the number of electrons, but sometimes they don't give you this, but you can tell the relative height is the number of electrons. So this is going to be 2s, 1s2, this is 2s2, then this is 2p6, and this is 3s2. So that's how you find your electron configuration from photoelectron spectroscope. There's really not much else to photoelectron spectroscopy except knowing how it works, but yeah, that's it. Alright, periodic trends, let's do it. Alright, let us go quickly what they're called. Alkali metals are on the left. They make 1+ ions because they only have one valence electron. These guys are called alkaline earth metals, if you couldn't see over here. And basically they lose 2 electrons to become 2+. Then you got your transition metals over here, which act really weird with their electrons, so I have no idea. They could be 2+, 4+, 3+, I don't know. Then you got all your non-metals over here. This over here is called metalloids. These guys are technically metals, but they're called post-transition metals. Then you got your non-metals, and you got your noble gases because they don't react with anything. This should be reviewed. Okay, now we gotta talk about trends. So first thing first, atomic radius. This thing was like pretty confusing to me because I was like, if you add electrons, why is it not getting bigger? Because it doesn't get bigger. Lithium is the biggest one in this row over here. What the heck? Well, the reason is, as you're adding electrons, they're all on the same energy sublevel, right? Like, if you're adding electrons, they're all on the second level. They're all in the second shell. So they're not really getting farther away. They're just like hanging out in that same shell. However, you are adding more protons. And if you have more positive charge in the nucleus, they're going to attract the electrons more. So just pull them in like Spider-Man, and boom, they get closer. Which is why, as you go from left to right, you're getting more protons. So it's bringing in the charges closer. So you get smaller atomic radius. However, as you go down, you do get another whole electron shell. And like the electrons inside that are shielding it. So like basically the valence electron of sodium, right? It's just hanging out there, and then all the other shells are on the inside. So all the other shells are going to block the charge of the nucleus from affecting this guy that's hanging out here. So essentially the nuclear charge gets canceled out by all the other electrons, and basically there's only one positive charge left that gets to the final charge. So essentially the effective nuclear charge, as it's called, is exactly the same. However, that one charge out here is on a whole nother energy level, so it's farther from the nucleus. So it has a bigger atomic radius. So basically as you go down, it increases in radius. As you go right, it decreases in radius. And okay, the best way to memorize trends is just to memorize the one that has the most extreme of them, okay? So which one has the biggest atomic radius? It's francium. So then, if you just want to remember it, you literally like, as it gets farther from francium, it gets smaller in radius. And as you get closer to francium, it becomes bigger in radius. That's how I like to think of it. If you just memorize the corners at which things increase, then you don't have to remember like separate for rows and columns. You just get close to francium. But another thing you got to consider are ions, right? So let's say you have Li and Li1+. Which one is bigger? Well, Li and Li1+ have the same number of protons, right? So they both have the same attractive force. However, if you take out electrons, like, it's for sure going to get smaller, right? Because you're just taking out electrons, but the attractive force stays the same. So you have less stuff that's hanging out on the outside. And then, of course, like, there's no electron-electron repulsions that are pushing them outward, right? If you take out one electron, then the rest of them are not pushed out by that electron. So essentially, if you take out electrons, but remain the same amount of protons, you actually decrease your atomic radius. So Li looks like this, boom, boom, and then you got one out here. Li1+ actually looks like this. So it's actually a lot smaller than this. So essentially, whenever you're dealing with ions, the more electrons, the worse. Like, the more electrons, the bigger it is. The less electrons, the smaller it is. That's all you gotta remember. Alright, ionization energy. Basically, it's like how easy it is to remove the first valence electron. So it's really easy for lithium, sodium, whatever, these guys, because they want to lose that electron. These guys kind of don't want to lose it, but they're okay with it, right? Because then they get a half-filled 1s orbital. That'd be kind of epic. So these guys have the next highest. Now, these guys are kind of sketch. You don't really have to worry about them. But these guys have higher because they're not getting anything special by losing an electron. It's kind of lame for them to lose an electron. So Basically, fluorine has the highest ionization energy, first ionization energy, because it does not want to lose an electron. It wants to gain an electron. But then as you go down the thing, like the final electron is farther and farther away from the nucleus, right? So it becomes even easier to take it away. So once again, francium has the lowest ionization energy because it takes the least amount of energy to get rid of that one electron. And then everything just decreases that way. Second ionization energy, you basically shift it over one because basically lithium gets the same as all the noble gases. Beryllium just becomes lithium once you take off an electron. Well, not exactly, okay, I know, but like they become similar in electron configuration. So essentially, your highest second ionization energy is going to be radium. And then we got electron affinity, which is basically the energy you release when you take in an electron. And for this one, I just really don't like thinking about it too much. But basically, chlorine releases the most amount of energy when you take in an electron because it just really wants to do it. So it just takes it in and boom, it's happy. It releases so much energy. So chlorine is the most. I don't know why it's not fluorine. It has something to do with like it being at the right distance from the nucleus or some stuff. I'm not exactly sure, but chlorine, just know it's chlorine as the most electron affinity, and as you get farther from it, it decreases. Electronegativity is basically how much it snatches electrons from other guys in a covalent bond. So fluorine, in this case, is the most because it wants that electron so badly. It has a very small atomic radius, so it's like closer to the electron, so it's just going to snatch it very much. And then it decreases as you get away from fluorine. And then just know how electronegativity affects bonds, right? So if you have one really electronegative element with a less electronegative element, it's going to be polar covalent. If it's really, really big, that difference, then it's going to be ionic, because one's just going to completely snatch the electron. If they're approximately equal, that's going to be a normal covalent bond. Epic. And last but not least, metallicity. Basically, the ones that are like, this has to get closer to francium, because francium is like very willing to give off its electrons. So francium has the highest metallicity, and as you get away from it, it decreases in metallicity. That one's like the most boring one. I don't know. That one's boring. But it exists. So there you go. Alrighty, thank you guys for watching. If you guys have any suggestions, please let me know, because this is new for me. I think it's working. I don't know. You guys tell me. A lot of you guys wanted AP Chem, but if there's a specific way in which you wanted it covered, please let me know. Please, I beg. But anyways, as always, thank you guys for watching. If you enjoyed the video, leave a like and subscribe for more. Thank you guys for watching again, and see you guys next time.